everyone. Now let us see next numerical for the root locus. According to the numerical, we want to plot the root locus for given open loop transfer function. And according to numerical, also comment on stability for the system and time domain response for the system. So in first step, we will calculate open loop poles for the system and open loop zeros for the system. We have two open loop poles for the system at s equal to minus 0.2 plus j 0.6. Second at s equal to minus 0.2 minus j 0.6. We have one open loop 0 for the system at s equal to minus 1. So we have two root locus branches for the system. Two branches of root locus start at open loop poles for k equal to 0 and terminate on the open loop zeros at s equal to minus 1 and s equal to infinity for k equal to infinity, because we have only one open loop 0 for the system. So one branch for the root locus terminates at s equal to minus 1 for k equal to infinity, and second branch terminates at s equal to infinity for k equal to infinity, because we have only one open loop 0 for the system. In fourth rule, we will decide existence of root locus on the real axis with the help of pole 0 diagram. So according to figure, we have a pole 0 diagram. We have first pole, we have second pole, we have only one 0 at s equal to minus 1 for the system. So if we consider point P1 between s equal to minus 0.2 and s equal to minus 1, we have two poles to the right of point P1. So we can say it is an even number. So P1 will not lie on the root locus on the real axis. Now consider point P2 beyond s equal to minus 1. If we calculate total number of poles and zeros to the right of point P2, we have 3 poles and zeros to the right of point P2. So we can say it is an odd number. So P2 will lie on the root locus on the real axis. So we can say root locus on the real axis exists between s equal to minus 1 and s equal to minus infinity. So we can say root locus on the real axis exists between s equal to minus 1 and s equal to minus infinity. In fifth step, we will calculate break in point, because here we don't have two successive poles on the real axis. So we can say we don't have a break away point. We have only break in point, because already I have told you in previous video class, if we have a 0 on the real axis and we have a root locus on real axis to left of that 0 and p greater than z, we can say there will be a break in point to left of that 0. Here we can say we have a break in point between s equal to minus 1 and s equal to minus infinity. We can calculate break in point with the help of same procedure according to characteristic equation. In general form, we can write characteristic equation with the help of 1 plus g of s h of s equal to 0. We know the value of g of s, h of s, put the value and solve for k in terms of s. Let us differentiate k with respect to s and put dk by ds equal to 0. So we have s equal to 0 and s equal to minus 2. S equal to 0, this is not a valid break-in point because we decided we have break-in point between s equal to minus 1 and s equal to infinity. So we can say s equal to minus 2 will define a valid break-in point because minus 2 will lie to the left of point s equal to minus 1, or minus 2 will lie between s equal to minus 1 and s equal to minus infinity. So minus 2 is our valid break-in point. In next rule, we will decide number of asymptotes with the help of p minus z. We have only one asymptote. We can also calculate centroid, but here we have only one asymptote, so no need to calculate the value of centroid. Centroid is the point of intersection of asymptote on the real axis. We have only one asymptote, so no need to calculate, but we can calculate with the help of formula. Already I have told you. So we have centroid value 0.6. In seventh rule, we will calculate angle of asymptote with the help of formula. Already I have told you. Here q we have only 0 because q will vary from 0 to p minus z minus 1. That's why here we have q equal to 0. So we have only one angle of asymptote. It is 180 degree. We can calculate with the help of formula after putting q equal to 0. Next step, we will calculate angle of departure because we have complex poles. So in eighth rule, we will calculate angle of departure from complex poles with the help of formula. Already I have told you, plus minus 180 degree plus phi. Phi we can calculate with the help of summation phi z minus summation phi p. So for calculating summation phi z and summation phi p, we will draw the pole 0 diagram. So here we have one pole at minus 0.2 plus j 0.6. We have second pole at s equal to minus 0.2 minus j 0.6. We have 1 0 at s equal to minus 1. And here first we will calculate angle of departure from complex pole minus 0.2 plus j 0.6 with the help of formula plus of 180 degree plus phi. Phi we can calculate with the help of summation phi z minus summation phi p. But here we have only one remaining pole and 1 0. That's why we can write phi equal to phi z minus phi p. So first to calculate phi p, we will join minus 0.2 minus j 0.6 with minus 0.2 plus j 0.6 because we are calculating angle of departure from complex pole minus 0.2 plus j 0.6. Suppose this is phi p. Directly we can write it is 90 degree. To calculate phi z, suppose this is angle phi z. So to calculate phi z, we will join 0 at s equal to minus 1 with pole where we want to calculate the angle of departure. Suppose this angle be phi z So we can calculate phi z with the help of tan inverse 0.6 divided by 0.8, because this value is 0.2. So this value becomes 0.8, and on imaginary axis this value is 0.6. So phi z, we have tan inverse 0.6 divided by 0.8. So we have phi equal to minus 53.13. So angle of departure from complex pole minus 0.2 plus j 0.6 is given by 180 degree minus 53.13. So we have 126.87 degree. Similarly, we can calculate angle of departure from complex pole minus 0.2 minus j 0.6 with the help of formula minus of 180 plus 5. That means minus of 126.87, because already we have calculated 180 plus 5. In 10th rule, we will calculate intersection point of root locus branch with the imaginary axis. So here we don't have intersection point, because asymptote will not cross the imaginary axis, because we have angle of asymptote 180 degree. So asymptote or straight line will not cross the imaginary axis. So we can say root locus branch will not cross the imaginary axis. So no need to define intersection point of root locus branch with imaginary axis. Now let us see how we can plot the root locus for the given open loop transfer function. So first we will draw the S-plane. Horizontal will define sigma, vertical will define j omega. We have one pole at s equal to minus 0.2 plus j 0.6. We have second pole at s equal to minus 0.2 minus j 0.6. We have one 0 at s equal to minus 1. Already we have decided we have root locus on the real axis between s equal to minus 1 and s equal to minus infinity. We calculated the value of centroid. It is 0.6. Already we calculated angle of asymptote. It is 180 degree. It is 180 degree. So we can say we will draw the asymptote at an angle of 180 degree from 0.6. So here dotted line will define asymptote at an angle of 180 degree from centroid, that means from 0.6. After that we will define starting and ending point for the root locus branch. Already we have decided according to third rule. So here root locus branch starts from minus 0.2 plus j 0.6 for k equal to 0. Similarly, second root locus branch starts from minus 0.2 minus j 0.6 for k equal to 0. Angle of departure already we have calculated. So root locus branch will depart at an angle of 126.87 degree. So calculate sorry, we already calculated angle of departure from complex pole. So root locus branch will depart at an angle of 126.87 degree from -0.2 plus j 0.6. आपको प्रोटेक्टर की हेल्प से मेजर करना है. सपोज दिस इज 126.87 degree. So first root locus branch फर्स्ट कॉम्प्लेक्स पोल से डिपार्ट होगी 126.87 डिग्री पर, 87 डिग्री पे. दिस इज माई फर्स्ट रूट लोकस ब्रांच. सेकेंड रूट लोकस ब्रांच विल डिपार्ट एट एन एंगल ऑफ -126.87 डिग्री. मेजर इन clockwise direction with the help of protector. Suppose this is -126.87 degree. So second root locus branch -126.87 degree पर डिपार्ट होगी फ्रॉम सेकेंड कॉम्प्लेक्स पोल. ऑलरेडी वी हैव कैलकुलेटेड ब्रेक इन पॉइंट. ब्रेक इन पॉइंट था -2 पर. दैट्स वाई दोनों रूट लोकस ब्रांच -2 पर एंटर करेंगी. एंटर करने के बाद एक रूट लोकस ब्रांच ओपन लूप 0 पर टर्मिनेट होगी फॉर k इक्वल टू इन्फिनिटी. सेकेंड रूट लोकस ब्रांच एस इक्वल टू इन्फिनिटी पर टर्मिनेट होगी फॉर k इक्वल टू इन्फिनिटी. So you can say this is my first root locus branch, this is my second root locus branch. So this is a root locus for the given system. Now let us see how we can decide the stability for the system. According to diagram, you can say for all values of k, for all positive values of k, roots lie in the left half of S plane. So system is a stable system. We can calculate the value of k at break in point, or we can calculate the value of k for s equal to -2 with the help of magnitude criteria. Value आएगी 3.6. So you can say for k equal to 3.6, we have a critically stable system or critically damped system. For k equal to 3.6, we have a critically stable system or critically damped system. Critically damped system. For k less than 3.6, what will happen? जब k की वैल्यू 3.6 से कम होगी, we have roots on this path. That means roots are complex conjugate. We also have roots on this path. So we can say for k less than 3.6, roots are complex conjugate. So system is under damped system. Third, for k greater than 3.6, what will happen? Roots will lie on the real axis, or you can say roots are real. So system is over damped system. For all values of k, that means for all the positive values of k, roots will lie in the left half of S plane, so system is stable. Let us calculate the value of k for s equal to -2. We have k 3.6, so we can say for k equal to 3.6, system is critically stable or critically damped system. You can calculate the value of k at s equal to -2 with the help of magnitude criteria. Already we calculated in previous numerical. For k less than 3.6, what will happen? Roots will lie on this path or on this path. So we can say roots are complex conjugate, so system is under damped system. For k greater than 3.6, what will happen? Roots will lie on the real axis, or you can say roots are real, so system is over damped system. Thank you.